Okay, so we're a little after 10 o'clock here today, and we'd like to thank everybody for joining Ridgetop Group and Distinguished Engineer James Hoffmeister on our webinar for our Adaptive Remaining Useful Life Estimator called ARULE. So today in the conference room, it is myself, Wyatt Pena, Director of Operations, James Hoffmeister, Christopher Curdy, and Jan Traficante. Any questions from attendees that may pop in during this webinar, we ask that those are held until the end, and we'll be happy to address those at the end or through email.
Today, we're going to cover the agenda for this webinar is we're going to do some introduction. We'll discuss some history and evolution of ARULE. We'll discuss and show examples of our graphical user interface that supports ARULE. We'll have some real-world examples. We'll have an ARULE demonstration, and we'll do a summary and questions and answers. This Ridgetop Group was formed around 2000. We're a technology leader in reliability engineering, condition-based maintenance, PHM, and integrated vehicle health management. We provide engineering design services, circuitry, and basically solutions to PHM problems that need to be solved. We are AS 9100 and ISO 9001 certified. Today, we're going to cover the scope and context of ARULE, and we're going to try to put it into the context of a framework. What you see here is a framework that is adopted by, and this is basically in compliance with that adopted by the IEEE PHM Society and the IEEE standards. You have a sensor framework, a feature vector framework, you have a prediction framework, you have a performance validation framework, and you have fault management. Today's webinar is not concerned with fault management. Fault management is really application dependent, and we're going to concentrate on ARULE that generates the prediction information that is necessary to support our fault management. Our ARULE is based upon what we call feature data. And we do that for a number of reasons. It's not practical for ARULE to provide a general sensor framework solution because that's basically, again, application dependent. It depends upon what sensors you're using. It depends upon what the failure mode is. It depends upon the construction and configuration of the system being monitored. And that's really not a general type of solution. So we're going to concentrate on the area that you see at the bottom there that sort of grew with a green background. That basically comprises ARULE. We process data, we control the processing of data to produce a prediction as to when something is likely to fail in some future time. Remaining useful life, state of health, prognostic horizon are the primary prognostic information. And in the real world, PHM systems are basically three stages. You have your hardware and your firmware, that's a sensing stage. Then you have a stage where you condition and you fuse data, you transform data, you perform all kinds of data processing. Then you take the result of the data processing and you do things like random walk, particle filtering, Kalman filtering, in order to come up with an estimate of a future time of failure. We call that the prognosing stage. Our ARULE core consists of the data processing and the prognosing stage. And you look down at below and you'll see that condition-based data is very noisy. It contains data that's not pertinent to a failure mode. It contains noise, it contains distortion, and it contains all kinds of variations having to do with the environment. Somehow that data has to be processed to produce what is shown in the middle there at the bottom, and that is the estimates themselves. That's a plot of the remaining useful life and the prognostic horizon and a plot of the state of health. That prognostic information then goes to a fault management stage. Next. To give you an example of the complexity of a sensor framework and how to extract feature data. The output seen at the upper right-hand side is a typical output from a switch mode power supply. It contains all kinds of information, some of which may be directly relatable to a failure mode, some of which are not. You'll see that there's effects of thermal, there's ripple voltage, damping response, there's all kinds of data. It's the job of the prognostic engineer or the sensor engineer to determine which of these features can be used in an efficient manner that is directly correlatable to a failure mode. For example, if you extract a ring-in response at the bottom left-hand side, it looks something like that. And it basically is whenever there's an abrupt change in current, that circuit tends to ring. And it's a damp ringing because you have feedback. That frequency, there's a natural resonant frequency. That natural resonant frequency, for example, is the result of the intrinsic capacitance and the explicit capacitance and inductance and resistance of the filter circuit of a power supply. And a common failure mode of power supplies is a loss of filtering capacitance, which results in a change of frequency. So if you can capture that damp ringing response and you can figure out what the frequency is, then you can capture the change in frequency and you can relate change in frequency to a loss of capacitance. That is what you do with a sensor framework. It's that change in frequency. The frequency itself is called feature data, and that's what our ARULE works on. So what we have is you have a noisy or with many features output of a power supply. You extract the ring-in response. The ring-in response has an amplitude. It has a period associated with the resonant frequency and has an exponential decay. Every one of those features can be used in prognostics. Our particular solution that we believe is the most efficient is to use the period, and we then convert that to frequency, and we use that to give an estimate. What you see there is ideally, before you even start, you will exactly guess how long it takes each and every item to fail. That's not going to happen. But ideally, you could. And then ideally, you will exactly make accurate estimates that is a straight line from initial value to end of life. That's ideal. That does not happen, and we will discuss that. Next. Okay, what really happens, the data that you see, even after you've done some initial data processing with your sensor framework, you have a noisy signature seen here at the bottom left-hand side. You can see that it changes, and it's changing there in response to, in this particular case, a force change or loss of filtering capacity. It was an experiment that we performed in our development. But that signature, that curvilinear signature, can be processed and linearized as shown by the FFS. That is, in fact, a transformed and conditioned version of the input shown on the lower left-hand side. That information is then passed off. The FFS is then passed off to our prediction framework. We convert the feature data to what we call the fault to failure progression. We convert the fault to failure progression data or form into a degradation progression signature. We then transform the DPS to a functional failure signature. And that functional failure signature is what is actually input into the second stage of our ARULE. Next. This is an example of ideal data, okay? And just to show why we do these transforms. What you see on the left-hand side is an ideal degradation, absent any kind of thermal noise, absent environmental variations, absent manufacturing variation. It's a nice, predictable curve. But even so, that data has an amplitude. The amplitude of every power supply, even of the same type, will be different. And so therefore, that's application dependent. And that's not good, because that means you would have to have a model for every single power supply in the world. Not practical. So what we want to do is we want to transform the data so that we have that we end up with a representation that is derived from the original data, yet the amplitude has been changed from, for example, voltage or power or frequency to a percentage. Now I only have one model. It's a percentage. And furthermore, the ideal model, it will be a straight line. If it's 0 or less, there's no degradation. If it's between 0 and 100%, it's degraded. When it reaches 100%, it's failed. That's a nice, easy model. And that's the model our ARULE uses. Okay, you can see, so now that you have the feature data, it consists of, for example, DC, noise, and small signal variation. The small signal variation is the first term on the FD equal model. And you can see that what we actually do is we take this data and we perform the FFP equals transform, and that gives us a dimensionless data. We then solve that data because that curve is really the result of a change in parameter or value of a parameter, or represented by dp over p. That is a derivative. And the nice thing about a derivative is that it linearizes curvilinear data. So we solve that. We solve that equation, and we have done that for 7 families of physics of failure models. And when you solve that equation and then use a solution, that will convert the curvilinear data into what you see on the right-hand side. And that slope of that signature is dependent upon, or is in direct correlation to, the failure mode. Next. So as an example, the data on the on the left-hand side, as you see there, is then transformed, and you can see that it in fact takes that data, that curvilinear data, and it linearizes it. It's still noisy because there's noise in the original data. So there's noise in the transform signature. Okay? We then take the DPS, which is linearized, and we convert that into, in other words, ratio. The degradation progression signature is ratio. We then convert that into percentage. And that's what we feed into the second stage of our ARULE, that data on the right-hand side. Next. So now we have now we're going to discuss the second stage, or the prediction framework of ARULE. NASA, we started off and we follow the NASA view, and the NASA view was remaining useful life, state of health, and accuracy was related to RUL. But the papers that NASA published revealed an anomaly, and that is that as you near the time where of end of life, the accuracy blew up. And that's because of the way they do it. They are taking the difference between actual and estimated and divided by actual. The problem is the actual goes to 0. It's an analog value. So now what you're taking is you're dividing a difference by 0. And that's not good. We do not do analog sampling. We do not do a sample once every femtosecond, for example. You sample once an hour, once a day. So now you have discrete data, which has a large variance, like it's the estimate is plus or minus 1 hour, and you're dividing by 1 second. Not good. So that's why it blew up. So what we did, we said, you can't do that. You can't divide by a value that approaches 0. So we use prognostic horizon, which NASA had defined. We say, what if we take the initial prognostic horizon and we define it in a manner that it's constant? Okay? Ideally, it's a constant value, as seen in the middle there at the bottom of the 2 plots. So now that is ideally a nice constant value. And prognostic horizon is the time it takes for it to fail. In other words, the current time plus your estimated time compared to the actual time. So now we have something that doesn't blow up. And that's what we do. Next, Ridgetop, the second stage. Over the years, our second stage, we feel, is state-of-the-art. In fact, best of breed. We use common-like filtering, which is we compare the input to a model, we adjust the model, and we use the adjusted model to make a prediction. We also use the principles of particle filtering. What that says is that rapid changes in magnitude and direction are not a true reflection of degradation, because degradation is not an instantaneous. Like when you put water on a stove, it doesn't instantly boil. Degradation, or the measured data, should not have rapid changes in magnitude or direction. That is a function of your measurement system. We also do fast convergence, and fast convergence means that it is impossible to accurately predict when something begins to fail. So you have to make an estimate, And that estimate, whatever estimate you make, will either be lower or higher than the actual. And we want to converge as rapidly as possible to the true time of solution. We also do random walk. And random walk, basically, what we do is we say, look, degradation does not increase and then decrease and increase and decrease and then hold constant with continued use. It has a tendency to go from 0 to a maximum value. Okay? So that's random walk, just like you're walking from one corner of a lot to the upper corner of a lot. Trending, we also know that the data that we're working with has a tendency to trend. Again, that's related to the fact that it's like a particle and it does not make rapid changes in direction. We have models, and we have reduced our models to no more than 5. We also have machine learning. So our engine that we have developed and that we use is very robust. It contains many, many algorithms. Every one of those is at least one algorithm. Next. Okay, over the years, this is the actual, in this particular example, the estimate is that they're going to take 200 what? 200 days, 200 years, 200 months, whatever. But that's not really, in this particular case, for this particular experiment, the actual failure time was almost 120. So we have basically an almost 50% error. The NASA method says that you should gradually change from your initial estimate and become increasingly accurate as you approach end of life. And that's basically what we did when we started back in 2006 and 2007. And we would produce data as shown by the dotted line. And as you can see that it gradually converges to the true value. But then we said, that's not really good because then what that says is that you don't really become 10% or 5% accurate to the very end. The military, for example, used to complain to conferences I went to, said, can't you guys do better than plus or minus 50%? So I said, okay, what we need to do is make a rapid convergence. And by the 2012, you can see we were producing estimates that more or less followed the solid red line. And in fact, we were so happy with that result that we used that version of the engine and we embedded it in one of our products called Sentinel power supply. And you'll see a demo of that. But we didn't stop there. Over time, it occurred to us that the data, that curve that we saw, was really a function of a change of parameter, dp. And if we could solve that curve in terms of dp over p, that gives us the derivative. And that linearizes the data. By 2018, we had perfected it, and we were now producing the solid black line estimates. The solid black line is when your estimate is about 50% higher, you can see what it does. And we rapidly convert to a true value. The dashed dot line is if your estimate is below. So we can rapidly converge from a high initial error or a low initial error. And we converge very well. So we had a very good engine by 2018. That engine, even though it had an application, an open source application programming interface, did require somebody to write a wrapper around it to use it, like our Sentinel Power. Well, in today's modern world, customers don't really want to write applications. So we said, okay, what we need to do is come up with a general application that can be used by our own Sentinel Power and by customers. So that's what we did. By 2020, we had embedded our engine into a program called User Data ARULE. But we didn't stop there. That used an end user interface, which nobody wants to use command lines. Okay, it's not user friendly and it's not intuitively obvious. So the Ridgetop team, Chris and myself and Wyatt, in fact, Chris and Wyatt designed the graphical user interface and they implemented it to use the UDA rule. And that works very, very well. And we have now used that. And that's what we're going to talk about and show you is basically the GUI and the UD ARULE. Next. Okay. I alluded to the fact that ARULE, it has an open source application programming interface, and there it is. ARULE is an object module. It has the signature processing, it has prognosis processing, and it has control and data flow. And so we take a piece of data, it gets passed to ARULE, ARULE works on it, and we put the output results into an input-output buffer. There's an API that's used to communicate between an external program and a ARULE interface. It's open source, it's well documented, it works, but it does require someone to write an external program that does initialization, housekeeping, set up the API, set up the IOB, put the data in, and all of that work that you see in the block on the left-hand side. What we did was we said that external program, let's write a general purpose user data version of that. Next. So this is now what it looks like. UD ARULE is basically performs the wrapper around the object module. UD ARULE, one of the things about end user applications is that to be useful is that UD ARULE needed to be table driven. Traditional tables are hard-coded programming tables, and that's not good because that means if you wanted to customize UD ARULE to work with your application, you would have to change the tables, recompile, and relink. Not good. So what we decided to do was, look, it'll be table driven because it has to be so you can customize it. And also so you can configure your system. So we came up with what we call definition files. Definition files is basically a human readable, machine readable script that defines tables. And those tables is what we use to control how we process data. Next. But those tables need to be updated. We alluded to the fact you need to update it, you need to maintain it. That of itself is not an easy thing to do. And that's where our graphical interface comes in. It basically performs a wrapper so that users can modify the tables, change the tables, delete them, use them without having to know a whole lot about how to do it, without having to say, well, I need to edit it, and I need to do these keywords, and I need to use the right parameter, the right values. And so our GUI takes care of that. It makes an user-friendly interface that is a wrapper around the definitions, which provides a table-driven capability that UD ARULE uses to input data into our ARULE two-stage engine. Okay, let's say yes. One of the other thing, of course, with GUI is the visualization. One of the things is that UD ARULE and ARULE itself produces data points. It's hard to envision what the data point looks like. So the best way to do that is to plot the data. Well, plotting of data can sometimes be non-trivial, but our graphical user interface provides that. And so that the user doesn't have to worry about, well, how do I look at the data? How do I know what the data looks like? How do I know whether or not I've chosen the right values for these tables, these definitions? Next. Our graphical user interface basically contains of input support and data output support. We call them tabs. Okay? The left-hand side is system definition input, and that shows you the system definition files and the node definition files. The output will provide the plots of the input data, RUL, and pH, the prognostic horizon, and state of health. Next. One of the things you do is you go ahead and you have to select a system. What we have developed is a method for users to develop definitions of systems that are of interest to them. We provide some built-in examples, and we should go through those examples. But users, those are intended to be used as examples for users to modify and/or to create their own versions that reflects their own particular system that they want to look at. So what you see here is at the very top on the right-hand side is a system definition. And this particular one has one node. And you can see that it's like a table, right? It says, here's our ID for it, and here's the file that defines what the system looks like. And when you look at that, you'll see that the node definition contains basically all of it is keyword, an operator, which is the equal sign, and the operand, the value for the operator. Okay, and you'll see at the very bottom there is a plot of the input that's going to, that represents a failure mode for a particular system. Next. One of the things you could do is, obviously, is to modify the system definition. Okay? And so these are the type of the panels and drop-down menus that our GUI provides for you. You can see that you selected that a system definition file. It points to a table as shown on the very top there with the right pointing arrow. And that then also the detail is shown below that. Next. That definition then points to one or more node definitions. And you'll see it on the panel here. You'll see that you've got, it consists of basically blocks of words like FDZ points. That represents a keyword, and the value is 10. And if you look, what that is in fact, a user-friendly view of what you see on the far right-hand side. Okay. That's the actual input. It's usable. It's a machine-readable form of a table, which is very good. It's also human-readable, so that you don't have to try to interpret machine language, which is all good, but it's not really user-friendly. Okay? You have to read it. You have to understand what all the values are, whereas the GUI takes care of that for you. Next. Okay, so what do we do? You can see here, and this is just an example. You'll see that data, it has values, okay? Unit measures value. So the first thing we want to do is take unit measure values and convert it to dimensionless ratios. We also want to transform or translate the DC value. You'll see the circle on the bottom circle on the far left. We want to take that and translate it to a zero reference. And that puts everything back to zero reference. That makes our modeling easier, makes our processing easier, which improves accuracy, because the more complicated processing you do, the more likely you are to make an error. The next thing you want, and you can also see that we provide parameters that will then allow you to specify how you want the data to be processed. Because, for example, a given power supply, it might be, and I'll just use a noise or a ripple voltage. As the power supply might say, ripple voltage is 0 to 100. So one power supply might be 0. Another power supply might be 50. The third power supply might be 100. That's all good. They're all within specs. But now that's 3 different models. So what we do is we will say, look, we will dynamically calculate for you what the nominal value is. Okay? And that's what's shown on the top right-hand side. We will then also take, once we've done all that, we will then take that curvilinear data, and you'll see here on the bottom left-hand side, we will take that transformed data and linearize it. And then we also have methods to further condition data to reduce the amount of noise and variation. And that all helps to improve accuracy. Next. One of the things that needs to, or what we use to measure is what we call pseudo-ideal. By pseudo-ideal, we mean that the data is ideal. It's noiseless. It's distortion-free. There's no effects of feedback. So it's a very nice and clean, and it conforms to a nice signature. But because you cannot accurately predict when something will, how long it will take for something to fail, you will always have an initial error. So you will always start, and then you have to converge to the actual. Okay? And one of the measurements of a prediction engine is how fast given on average, how fast will it take you to converge to within 10% or 5% accuracy? For example, if a system will fail in 100 samples and it takes you 90 samples to converge to 10%, that means that you're pretty close to failure before you get 10% accurate. But if your system converges on average to the true solution with only 10 samples, that's much better than 90 samples. So that is a measure of accuracy. ARULE also has things, for example, machine learning. On the very bottom set of plots, the far left plot is input. And what that represents is a system that has been degraded. And at some point, the system is replaced. It starts off as non-degraded. So you'll see it'll start to degrade, and then sharp back down to nominal, and then it continues to degrade again. Without machine learning, what will happen is you'll see the results on the middle plot. Okay? All we know is what it was the initial estimated time of failure. But with machine learning, we will remember how long it actually took to fail, or what our estimate was when we first processed the data. And you'll end up with the result on the lower right-hand side. And you can see that that the second time around, once we've gone through it once, we remember the solution and the previous solution, and we use that result in the next time version. And that is what machine learning is all about. Next. Okay, so this is an example, a real example of the results produced by our GUI. You'll see that the top plot, that represents the input. The bottom plot is the state of health estimates produced by ARULE, and the bottom set of plots, the red line is prognostic horizon, and the black line is remaining useful life. And you can compare that to the pseudo-ideal. And you can see that we come out pretty darn close. Okay? How close do we come? It depends upon the size of the initial error, and it depends upon the noise of the input data. Our package, when you obtain our ARULE package, or UD ARULE, we have two demonstrations, Demo 1 and Demo 2. We use Demo 1 in this presentation. What you saw was the actual captures of the results of running Demo 1. Demo 1 is basically using the data at one node. Demo 2 is same as Demo 1, but we have two nodes. In addition to these two demonstrations, we have 9 real-world examples. And this comprises data that we have collected through experimentation, through historic use, and also through simulation. Transmitted power. A common failure mode of, say, a radar system or a radio system is loss of transmitted power. And you can take that loss and you can take the inverse of it, and you can show that you have an increasing loss. That data, which we ran as a simulation experiment for a radar system, produces the results shown on the right-hand side. State of health, that's the fault of failure descriptor. That's the intermediate result of processing the input data on the top left-hand side. Okay. So you can see that we have sort of gotten rid of the noise. And that's the input to the second stage. And it produced the state of health information seen in the middle plot, and the RUL and the prognostic horizon on the bottom plot. You notice that there's a great big difference between true prognostic horizon and the initial estimate. Next slide. If you reduce your initial estimate, this is the same data. This example here is exactly the same data, but now take a look at the output. We convert really, really fast. So when people say, how fast does ARULE take to converge? The answer is, it depends upon the noise, the magnitude of your initial estimate error. Next. Another real world example that we ran was we had created, this is Sentinel. we ran an experiment in conjunction working with NASA on our sensor solution for a pinion gear of a gearbox of a helicopter. You'll see on the bottom left-hand side, that's the data. That black data is basically the result of doing time sequence averaging of the data we collect. That is basically what is commonly referred to as an envelope. We then took that envelope and we converted it into, or input that, the envelope, the magnitude of the envelope, into ARULE, into our UD ARULE, and you'll see the results there. The top blue line is basically the data, the time sequence average data, and the black line is the state of health, and the red and black line on the very bottom is prognostic rising and remaining useful life. And you say, well, that looks sort of noisy, but that actually represents what actually happened, because it was taking so long for the gear to fail that we stopped the experiment, we took the gear out, and we damaged it by firing. Then we reinstalled the gear and then restarted the experiment. And when we did that, because now the gear, even though it followed, was rough, so now it's sort of like added some friction, which then caused it not to slip anymore, which then made it look like it was running real good. And that's that first glitch that you see. That's when we first took the gear out. Later on, we said, well, it still takes you too long. I mean, we can't sit here and run the experiment for 6 months. So we took the gear out a second time and followed it even further, reinstalled it, and then restarted the experiment. And again, you'll see the glitch. And that second time around is when it really started to fail. So the data produced by ARULE actually reflected what was really happening with the system.
And I think one other key point here is the slope of the state of health curve. Each time after the gear tooth was further damaged, it starts to accelerate further down each time at a faster rate.
And that's what really happens in the real world. When degradation starts and things begin to go from an inelastic to a plastic state, for example, it's a very slow process. It's sort of like when you take a paper clip and you bend it, and you keep doing that, and all of a sudden it becomes easier and easier to bend it, and all of a sudden it breaks in half. As plastic work, what I refer to as plastic work, as it progresses, the rate of degradation increases, the state of health starts to decrease or accelerate towards zero very rapidly. We then just took the data and we said, okay, let's just take the second part. Let's start with the point at which the data we had was where the tooth had become really damaged, okay? And let's just take that and run it through ARULE. And this is the result of just processing the circled data. Okay? Now, we threw out all the intermediate data, just kept the last part, and you can see that that is, in fact, basically real world, right? That is what would really happen if you were to run a system from zero to failure. You can see that if you look on the middle, you'll see some picture there of the pinion gear. The very first area, the far left-hand plot, you'll see on the right-hand ridges there, a slight filing. That was the initial state of damage. Eventually, when the gear failed, you could see that the tooth broke. And when the tooth broke, that's when the experiment stopped. One of the things about prognostic health management is you should not, and even though we did it here where we ran into actual failure of the tooth, the gear itself hadn't failed because it was still usable. It was rough, it was noisy, but it was still usable. Sort of like a tire that's half flat. It's not totally failed. In this case here, the gear tooth was not totally failed, but it had one broken tooth. So one of the things about prognostic health management is, at what level of damage do you say any further damage is unacceptable and I'm going to consider it failed? That is something that is basically application dependent, because it's sort of like the Energizer running bunny rabbit, right? Well, I can run it till almost the battery's dead. But if that battery used in a heart monitor, I don't want to wait until the battery's almost dead. That is in fact one of the hardest things about fault management is determining the difference between functional failure and physical failure.
Good point on
Yeah.
ARULE too is we actually get to specify that level of functional failure
Yes.
in our data set.
Yes. One of the parameters that we provide is to allow the user or the health management engineer to specify at what level of degradation ARULE could say it is functionally failed.
The key point here, I can handle this slide, Hoppy,
Yeah.
is really just showing the early development of what we call sentinel motion. So the experimentation and the work we were doing with NASA and looking at that gearbox fault in a helicopter gearbox system was really the development of what we call RotoSense, which is our IoT accelerometer and temperature sensor. And you can see we package that as in a form that we call the Sentinel Motion Toolbox or Sentinel Motion Development Kit. And that can be used as an R&D tool for data acquisition for industrial applications. And you can take that same type of data in the case we did with the NASA experiment, the time sequencing and averaging signal, and do prognostic analytics or predictive analytics with ARULE. And this slide kind of just captures that visual here.
This represents, we've discussed this about a power supply. There are two types of filters in power supply. One is called a half pi, which is basically an inductor and a capacitor. And the other one is called a full pi, which is a capacitor, inductor, and capacitor. This particular example is the ripple voltage as the output capacitance of a full pi filter fail. You can see that instead of being convex, it's concave. So it's a different type of curve, but we can handle that. We can handle both of the curves, and you can see that we convert that curve into, we have linearized it on the top plot on the right-hand side. There's the state of health estimates, and there are the prognostic horizon in red and the RUL estimates in black. Next, robustness. Again, this is, we have basically taken data and we have tried to linearize it. You have to know basically the curve. Is it a power function? Is it an exponential function? Is it a power function? Is it greater than 1 or less than 1? No, it's and what we did was we ran a series of experiments where we said, okay, I'm going to take the same input data and we're going to change the power. In this case here, the power is 0.4, 0.6, and 0.8. You can see that every one of those values produced reasonable estimates of state of health, prognostic horizon, remaining useful life. So that shows the robustness of our engine. You don't have to be exact. Next. This here, again, one of our real-world examples is, again, a switchboard power supply. And you can see that the curve is different. And in this particular case, we were actually removing capacitance by switching them out through a series program-controlled relays. And you can see the very different shape of the curve and the step functions. Again, look at the output. ARULE, the first stage, produced the output you'll see on the top right-hand side, and that was then fed into the second stage, which then produced the output that you see below it. Again, very, very, very good linearization, very good, very accurate estimates. Next. This one here, we also had a solution for the Navy where we investigated whether or not you could use capacitor leakage as a prognostic indicator. And we collected the data. The data in here was more or less linear, as opposed to curvilinear. And it doesn't matter. ARULE engine, with the definition of the table-driven processing, we were able to say, okay, take the linear data. We basically left it alone. And now we have the state of health, RUL, and pH results. And now what we have shown in here, you'll see that there's a little perturbation on the bottom set of plots on the right-hand side. And that is the result of a perturbation in the input data. So again, our engine basically follows or is producing estimates that correspond to the data, condition-based data. The NASA ran a series of experiments and they published the data. And one of their experiments was using the changes in internal battery resistance. Okay? So we took that data and from using what they had published, we produced an input data set that represented the NASA data. We then ran it through our UDA rule and our GUI support for it, and we produced the output shown on the right-hand set of plots. The other experiment that NASA ran was using loss of charge. You'll see there on the very bottom, on the left-hand side, that is a NASA published data. Okay? We took that NASA published data and we converted it into a set of input data as seen on the top. We then ran that input data into our ARULE and GUI port. Our ARULE product produced the output shown on the right-hand side. Again, very similar to all the other examples. So this is different problems, different data, we're producing consistent, accurate results. Next, on this example, had to do with the high data rate cables. And this particular cable was the cable that connected the transmitter to the antenna of a mast in a submarine sail that would be raised up and down. At that time, the action of raising the cable up and down, in other words, reading out and reading it in, caused it to be kinked. And the kink eventually results in broken internal strands and therefore loss of data. And we were asked to, if it was possible to set up a system to detect the damage, prognose when it was going to fail without having to take this antenna off a submarine, because it's hard to measure the cable that's inside the sail of a submarine. What you actually have to do is lift the antenna out with a crane. And you just can't take even a measuring time to measure resistance. You're not going to detect broken strands. So we devised a method where we're very similar to time domain reflectometry. This was frequency domain reflectometry. And we're able to not only detect damage of broken strands as indicated by the difference between the bottom set of plots on the left-hand side, which is undamaged. And what you see there is the three peaks when the data is transmitted, when it's reflected, and when it's received. And you can see the difference between that reflection plot and the reflection plot of a damaged cable. We then took the peaks of that, of one of those, as it changed from no peak, and as the peak got higher and higher, and we ran it through ARULE, and we produced the results shown. Again, consistent, very accurate. Next, this was our last example. It was a very complicated one. It was for NASA. What we were charged with was to see if we could set up to a PHM system to detect damage to an electromechanical actuator. And the damage was a power supply. It was the damage to the switching transistors, damage to the stator windings of the motor, load errors or friction errors on the shaft. Next, the little diagram showed, and you can see our UDA rule. You can see basically how we extracted the data, we processed the data, and the data that we looked, this was the power supply. You'll see it on the top left-hand side. It produced the results shown on the right-hand side. Again, consistent, very accurate.
And another key point on this particular real-world example is the way we defined multiple subsystems within the EMA itself. So that's done by specifying the number of nodes in the EMA system itself, and then using the node definition files to point to each of those individual input data sets.
The data that we collected, which was current sense data, was in fact very, very noisy. As you can see on the second figure on the left-hand side. Very, very noisy. Even by using windowing to eliminate the start and stopping of the actuator, the data is still noisy, full of harmonic. Our solution was able to do that. In fact, we were able to detect changes in current in the milliamp range, given a phase variation in the hundreds of milliamps range. We were able to isolate that milliamp change out of 100 milliamp plus noise. Next, you can see that our technique resulted in a feature data as shown on the left-hand side on the left, and which we then combined and further fused to produce the data shown on the right-hand side of the left. That's one failure. That's a failure mode of the switching transistor. The next on the right-hand side on the top is the failure mode associated with one winding of the stator. And on the bottom is the failure mode or the signature, if you will, when you have a common mode of failure, which is this rotating shaft. Next. Again, the results that show the results are good. Next. And next, these are all just showing you that we were able to process all the data from the different failure modes and we produce all similar results. Demo.
Yeah, next we'll cover ARULE demonstrated within our Sentinel Power product line. And this is what we would call the embedded version of ARULE in our Smart Probe 4000. So the examples, real world examples that Hoppy just covered are in our ARULE Graphical User Interface program, which is very good and a version of a standalone predictive analytics software package. So with that, the user is able to specify the definition files and analyze or post-analyze their data for prognostic estimates of remaining useful life and state of health. So as long as your input data sets or feature data sets are tied to a failure mode, you'll get meaningful estimates on that. So this particular demo is, again, what we'd call the embedded version. So with that, we have programmable capacitance degradation device, PCDD, the Smart Probe 4000, and a PC power supply system shown here hooked up to a laptop. So this is an accelerated window of or recording of the 7-minute demonstration. So I think this one runs in about 30 seconds, where you can see here, we're looking at the change in the bring down frequency of this particular power supply. And as that changes, we can see our state of health and remaining useful life plots happening in real time as this data is coming in. So it'll run its course here and state of health eventually gets down to a point of 0. And our change in frequency, which is our input data set, it constantly increases to that point of functional failure. So with that, again, the embedded version of ARULE is taking and sampling the data from Smart Probe and processing it, and we're interfacing this with our Sentinel PowerView software platform. So this is kind of just another visual of that, where the state of health again progresses from 100% down to 0. I actually believe this is one of the real world examples in our ARULE GUI package as well. So again, our feature data of interest that we were looking at was the change in the ring down frequency, which then yields condition-based data signature as shown here on the right. And this is all done within our Smart Probe 4000. But as Hoppy has mentioned earlier, there's other types of feature data that can also be monitored and diagnosed with these types of methods. So things like harmonic distortion, ripple voltage, damped ringing response, etc. So a brief recap, ARULE is a powerful prognostic reasoner and is available as a standalone predictive analytics software package that can analyze arbitrary condition-based data input. So that CBD data, as long as it's tied to a failure mode of interest, is going to give you those meaningful estimates of remaining useful life, prognostic horizon, and state of health. So ARULE can also be embedded in a complete PHM system level solution as demonstrated with Sentinel Power. And ARULE and some of the other Ridgetop algorithms, in particular MVA, are key elements in our Sentinel Suite family of Ridgetop condition-based maintenance, prognostic health management, and integrated vehicle health management solutions. So Hoppy, you want to do a brief recap on the overall summary here?
We introduced and we discussed the PHM framework which is the IEEE standard compliant. We discussed how it applied to ARULE. We talked about sensors versus a data node. We talked about ideal versus pseudo-ideal versus real, noisy, distorted. We briefly discussed the history and evolution of ARULE, starting from around 2006 to the present year. So there's been 16 years of continuous improvement in accuracy, in flexibility, in robustness of our ARULE, including our ARULE buoy operation, which provides wrapper, if you will, to assist in a user-friendly manner, creation and maintenance of system and node definitions, and also how to run the data. We showed 9 real-world examples, and we believe we have shown that ARULE is complex software to process complex condition-based data, which is robust, flexible, versatile, it's very accurate. That's the brief.
So with that, thank you, Hoppy, for going into this detail on ARULE. I know we've been planning this webinar for some time, and I believe it gave a great recap on the most recent work and developments we've been doing. So with that, I'd like to say a special thank you. And if there's any questions, we can take those via email. And we're also happy to be conducting software evaluation trials with anybody that's interested in that. So if you have any technology inquiries or business inquiries, feel free to reach out to any of us here at Ridgetop, and we'll get back to you as soon as we can. So thank you.